Okay, so today I've adjusted my audio just a little bit so that we're not popping as much. I don't know whether or not that helps, but we'll see. Just trying to refrain from having to put too much effort into editing these. Takes me away from actually focusing on the material itself. Um, so I have something new. So I found that the LLM was actually quite useful in helping me at least navigate um, through the code. So I built a little front end for this to actually, uh, it's like so that we can actually see things better, right? Like using Llama from the terminal is fun and all, but it's kind of hard to read. At least here we can actually have a richer conversation. My UI kind of sucks, but yeah, we'll get there. So I've kind of used RAG, so retrieval augmented generation, to load up some of the Linux kernel and C programming PDFs. So it actually understands like what we're trying to do more than its stock form. We could also like do some code here, so int main whatever. We could also have some bold text, and we could also do markdown that way. So I made all of this. So I'm pretty proud of it. We can start using it going forward, and have it try to help us navigate through the code base a little bit. Yeah. So let's continue on. Again, I'm not too like I really don't remember exactly where we left off. I think it was like right here. So let's go to policy. Okay. So policy. Policy is the behavior of the scheduler. Am I recording? Yes. Policy is the behavior of the scheduler that determines what runs when. A scheduler's policy often determines the overall feel of a system and is responsible for optimally utilizing processor time. Therefore, it is very important. I/O bound versus processor bound processes. Processes can be classified as either I/O bound or processor bound. Okay, so either your processes can be limited by either input output, so like writing to disk, reading disk, network, things like that, or compute, doing some long running calculation. The former being I/O bound, is characterized as a process that spends much of its time submitting and waiting on I/O requests. Consequently, such a process is runnable only for short durations because it eventually blocks waiting on more I/O. Here, by I/O, we mean any type of blockable resource, such as keyboard input or network I/O, and not just disk I/O. So, keyboard input is also a form of I/O that can block. Most graphical user interface or GUI applications, for example, are I/O bound, even if they never read from or write to the disk, because they spend most of their time waiting on user interaction via the keyboard and mouse. Conversely, processor-bound processes spend much of their time executing code. They tend to run until they are preempted because they do not block on I/O requests very often. Because they are not I/O driven, however, system response does not dictate that the scheduler run them often. A scheduler policy for processor-bound processes therefore tends to run such processes less frequently but for longer duration. Okay, so a scheduler policy for processor-bound processes. So anything that's more compute heavy in this case, they run less frequently, but they run for much longer durations each time. The ultimate example of a processor-bound process is one executing an infinite loop. More palatable examples include programs that perform a lot of mathematical calculations, such as SSH keygen or MATLAB. Of course, these classifications are not mutually exclusive. Processes can exhibit both behaviors simultaneously. The X Windows server, for example, is both processor and I/O intense. Other processes can be I/O bound but dive into periods of intense processor action. A good example of this is a word processor, which normally sits waiting for key presses, but at any moment might peg the processor in a rabid fit of spell checking or macro calculation. The scheduling policy in a system must attempt to satisfy two conflicting goals. So first, you need to satisfy process response time, so have low latency, and maximal system utilization, high throughput. Basically, do as much work as possible, never, I guess, idle, always get as much work done. To satisfy these at odds requirements, schedulers often employ complex algorithms to determine the most worthwhile process to run while not compromising fairness to other lower priority processes. The scheduler policy in Unix systems tend to explicitly favor I/O-bound processes, thus providing good process response time. Okay, Linux, aiming to provide good interactive response and desktop performance, optimizes for process response, which is low latency, uh, thus favoring I/O-bound processes over processor-bound processors. So keyboard input is like a higher priority in the Linux kernel because you want to, as you're typing on the keyboard, you want to be as responsive as possible. So you want to address these keystrokes. Yeah. So as we will see, this is done in a creative manner that does not neglect processor-bound processes. Interesting. So Linux does treats keyboard input with a priority in such a way that uh, it doesn't, I guess, it doesn't allow processor-bound processes, so compute-bound processes, to take a hit or a penalty in performance. So okay, so let's study some process priority. Uh, Process priority. A common type of scheduling algorithm is priority-based scheduling. So that's like the common type. The the goal is to rank processes based on their worth and need for processor time. The general idea, which isn't exactly implemented on Linux, is that processes with a higher priority run before those with a lower priority. Okay, so Linux doesn't exactly implement it in this way, whereas processes with the same priority are scheduled round robin, one after the next, repeating. So A, B, C, A, B, C, A, B, C. On some systems, processes with a higher priority also receive a longer time slice. The runnable process with time slice remaining and the highest priority always runs. Both the user and the system can set a process's priority to influence the scheduling behavior of the system. Okay, I think the statement is kind of important. So, when we're setting the process priority to try and kind of make some process a higher priority for the kernel's process scheduler to execute it, you have 2 points of control. User, so us, the user or the user space code, and then the system, the kernel, can set that priority of a specific process. Now, notice how it says influence the scheduling behavior of the system. That means, like, let's say as a user, if we set a process to run at like the highest priority, right? That is not going to say that the process runs at the highest priority. It's like we're influencing the process to run at a higher priority than what is normally, or what it normally runs. And so the system does that too, because actually there's like a calculation involved in actually prioritizing this process. So it's going to go on to that, but just know that setting the priority of a process, especially through like nice values, aren't it's not actually going to like guarantee that the process runs at your nice value. It just influences the total calculation of how the kernel determines whether or not your process runs at a specific priority. So something to know. Uh, the Linux kernel implements two separate priority ranges. The first is the nice value, a number from -20 to 19 with a default of 0. Larger nice values correspond to a lower priority. You are being nice to the other processes in the system. Processes with a lower nice value or higher priority receive a larger proportion of the system's processor compared to processes with a higher nice value, lower priority. Nice values are the standard priority range used in all Unix systems, although different Unix systems apply them in different ways, reflective of their individual scheduling algorithms. Okay, in other Unix-based systems such as Mac OS X, the nice value is a control over the absolute time slice allotted to the process. So in Mac, it influences the time slice. In Linux, it is a control over the proportion of the time slice. You can see a list of the processes on your system and the respective nice values under the column marked NI with the command PSEL. Okay, let's do it. So if we were to, let's just do a different terminal window, ps-el. Okay, so we get a bunch of processes, and then eventually we should have an I right here, this nice value. So the higher the nice value, think of it as nice, right? Like the lower priority you want your process to run. So technically, 0 is like neutral, and then -20 is like the ultimate highest priority. And remember, the book said that K-worker or these types of processes are kernel level, and since it's -20, it's like it's not nice. It's not nice at all. So it's probably running at like the highest priority process possible. So we take a look at something else. For example, K huge page D. That's like a lower priority. Or yeah, that's like the lowest priority. And then maybe something that is interesting here. Something different. Let's look for something different. So we have our old llama here. It runs at a normal priority. Bluetooth stuff runs at a normal priority. We also have right here, KRF command, whatever is -10. Polybar runs at 0, normal. Pipewire, which is our sound, right, runs at -11, which is a pretty high priority. So like yeah, you guys get the gist basically. So this you can actually see what exactly the nice value of specific processes are here. So okay. So okay, oh this is interesting. The second range is the real-time priority. The values are configurable, but by default range from 0 to 99 inclusive. Opposite from nice values, higher real-time priority values correspond to a greater priority. So whereas with nice values, where the lower the nice value is, the higher priority is because you're less nice. But with the priority, the real-time priority value, the higher the real-time priority value is, the higher priority it is. So all real-time processes are at a higher priority than normal processes. That is, the real-time priority and nice values are disjoint value spaces. So there are two separate things. So yeah, so they're not used together. Basically, they are used separately. Um, so basically, all the real-time stuff is at a higher priority, and then you do all the nice processes. Linux implements real-time priorities in accordance with the relevant Unix standards, specifically POSIX.1b. All modern Unix systems implement a similar scheme. You can see a list of the processes on your system and their respective real-time priority under the column marked RT-prio with the command. Whoa. Okay. ps-eo state uid pid ppid RT-prio time and com. Okay. Let's do it. Let's run it. So this is the process name I get. Yeah, it is com from the task struct. This one is a real-time priority. Cool. Okay. So let's execute that. Okay. So going up here, set that RT prio goes from 0 to 99. I don't know why this is not considered real time. Migration 99. Okay. Oh, command. Oh, that's what it means. Oh, command. Okay. So com in the task route corresponds to command. I think they mentioned that before. I'm a little dense. I couldn't pick that one up. So yeah, you'll see a bunch of like 50s, ones, 99s. Okay, sure. I mean, I'll take it as it is. I don't really care too much. I am guessing that these dashes here are all corresponding probably to the nice version. So let's take a look at like migration /5. If we were to look at stuff here, I don't know if this also exists. Maybe not. I don't know. Should we try to find it? Nah, it's not important for this. But yeah, we'll have some that are not even considered a real-time process in this case. So, okay. Oh, it says right here. A value of hyphen or dash means that the process is not real time. Cool. Okay. Okay. Time slice. The time slice is a numeric value that represents how long a task can run until it is preempted. The time slice is a numeric value that represents how long a task can run until it is forced to go back to the queue. Preempted. The scheduler policy must dictate a default time slice, which is not a trivial exercise. Okay, this is going to be hard. The scheduler policy must dictate a default time slice. So, okay, we get a default time slice, but it is not easy. Okay, too long a time slice causes the system to have poor interactive performance. Okay, the system will no longer feel as if applications are concurrently executed. Okay, so if each process has too long of a time slice to execute each time, like things like your mouse and your keyboard responsiveness is gonna take like it's gonna tank because it's not switching fast enough. Like the process, remember, like processes are switched preempted so often, so quickly that it makes you feel like things are concurrent. So longer time slices for the current task, pretty much, is gonna actually cause your system to feel like things are no longer running concurrently. While too short a time slice causes significant amounts of processor time to be wasted on the overhead of switching processes because of a significant percentage of the system's time is spent switching from one process with a short time slice to the next. So yeah, if it's too short, the system just wastes all its time doing context switches, like taking like putting registers back in and out, and by the time like it's done doing all that, time slice is done. So there's like no progress is made at that point. Um, so furthermore, the conflicting goals of I/O bound versus processor bound processes again arise. I/O bound processes do not need longer time slices. Why? Because they are waiting for I/O to finish. That's the reason why they don't need long time slices. Although they do like to run often, maybe check up to see if the I/O is done. Whereas processor-bound processes crave long time slices. It's to keep the caches hot, the CPU cache. Maybe I would assume. With this argument, it would seem that any long time slice would result in poor interactive performance. In many operating systems, this observation is taken to heart, and the default time slice is rather low. For example, 10 milliseconds. Linux's CFS scheduler, however, does not directly assign time slices to processes. Okay. Instead, so CFS does not completely give time slices to tasks. Instead, in a novel approach, CFS assigns processes a proportion of the processor. What the heck does that mean? Okay. On Linux, therefore, the amount of processor time that a process receives is a function of the load of the system. Oh, it's based on how busy the system is. So if the system isn't that busy, then the task is able to run longer. Which makes sense because as soon as the system becomes busier, probably then the preemption will occur to try and make up for like the responsiveness. Okay. This assigned proportion is further affected by each process's nice value. The nice value acts as a weight, changing the proportion of the processor time to each process receives. So yes, so nice values, although it's like a factor into the process scheduling, it exactly isn't. It is still very like useful in that it helps with that proportion, the, the 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 proportion of CPU time a process gets. Okay, processes with higher nice values, basically a lower priority, receive a deflationary weight, yielding them a smaller proportion of the processor. Processes with smaller nice values, which is a higher priority, including the negative ones, receive an inflationary weight, netting them a larger proportion of the processor. As mentioned, the Linux operating system is preemptive. When a processor enters the runnable state, it becomes eligible to run. In most operating systems, whether the process runs immediately, in most operating systems, whether the process runs immediately, preempting the currently running process is a function of the process's priority and available time slice. In Linux, under the new CFS scheduler, the decision is a function of how much a proportion of the processor the newly runnable processor has consumed. The newly runnable process? Maybe the newly runnable process has consumed. If it has consumed a smaller proportion of the processor than the currently executing process, it runs immediately, preempting the current process. If not, it'll schedule to run at a later time. So it's like, think of it as like a catching up or makeup. Okay. So here's how we think about scheduling policy. Let's see. Okay. Consider a system with two runnable tasks, a text editor and a video encoder. The text editor is I/O bound because it spends nearly all its time waiting for user key presses. No matter how fast the user types, it is not that fast. True. Because a user probably like types at most like maybe, I don't know, every 100, 200 milliseconds at best. That's a long time for a computer. Despite this, when the text editor does receive a key press, the user expects the editor to respond immediately. Conversely, the video encoder is processor bound. Aside from reading the raw data stream from the disk and later writing the resulting video, the encoder spends all its time applying the video codec to the raw data, easily consuming 100% of the processor. The video encoder does not have any strong constraints on when it runs. If it started running now or in half a second, the user could not tell and would not care. Of course, the sooner it finishes, the better, but latency is not a primary concern. So latency, when the author says latency here, I think they're saying like responsiveness is not a primary concern. So in this scenario, ideally, the scheduler gives the text editor a larger proportion of the available processor than the video encoder. Okay, so it gives the text editor a larger proportion of the available processor than the video encoder, which makes sense because it wants to be responsive. Because the text editor is interactive, we have two goals for the text editor. First, we want it to have a large amount of processor time available to it, not because it needs a lot of processor, but because we want it to always have processor time available the moment it needs it. Okay, so it has to always be ready to run. Okay. Second, we want the text editor to preempt the video encoder the moment it wakes up, say when a user presses a key. This can ensure the text editor has good interactive performance and is responsive to user input. On most operating systems, the goals These goals are accomplished, if at all, by giving the text editor a higher priority and larger time slice than the video encoder. Okay. Advanced operating systems do this automatically by detecting that the text editor is interactive. So how does Linux do it? Linux achieves these goals too, but by different means. Instead of assigning the text editor a specific priority and time slice, it guarantees the text editor a specific proportion of the processor. Okay. If the video encoder and text editor are the only running processes and both are at the same nice level, this proportion will be 50% each. So each would be guaranteed half of the processor's time. But because the text editor spends most of its time blocked waiting for user key presses, it does not use anywhere near 50% of that processor. Conversely, the video encoder is free to use more than its allotted 50%, enabling it to finish encoding quickly. Okay, so it's not locked in. The kernel's scheduler will actually give more processor time to the other process as it needs if the other process isn't really using it. So like even though like the text editor demands processor time like immediately, it's not always in need of it. So the Linux scheduler is, or at least the CFS scheduler is going to just give more time to the video encoder, but always be like ready to when the text editor does need it, it'll give priority to that text editor right away. Okay. The crucial concept is what happens when the text editor wakes up. Our primary goal is to ensure it runs immediately upon user input. In this case, when the editor wakes up, CFS notes that it is allotted 50% of the processor, but it has used considerably less. Specifically, CFS determines that the text editor has run for less time than the video encoder. So, like when the text editor needs the processor time, CFS will go, okay, well, you need the processor time, but by the way, how much processor have you used since you've been around? Oh, a lot less. Okay, sure. Um, so attempting to give all processes a fair share of the processor, the scheduler then preempts the video encoder and enables the text editor to run. The text editor runs, quickly processes the user key press, and again sleeps, waiting for more input. As the text editor has not consumed its allotted 50%, we continue in this manner, with CFS always enabling the text editor to run when it wants and the video encoder to run the rest of the time. So because it doesn't really use a 50% when it needs it, it always has that processor time available in its bank to just use and go, hey processor, like give this to me. I need it now. Okay. I'm guessing it's a different story if it's constantly using it, then it has to like get its fair share later. But since it was given 50% and it doesn't really use the 50%, it has every right to use it whenever it wants to. I think that's like the train of thought. Yeah. Okay, so I wonder if we ever get to code here. All right. Okay, so in the Linux scheduling algorithm, in the previous sections, we discussed process scheduling in the abstract with only occasional mention of how Linux applies a given concept to reality. With the foundation of scheduling now built, we can dive into Linux's process scheduler. Oh, okay, so this is the real stuff now. Okay. So scheduler classes. The Linux scheduler is modular, enabling different algorithms to schedule different types of processes. This modularity is called scheduler classes. Okay, so we can hook up different types of schedulers in Linux. It doesn't. I guess it doesn't have to be the CFS. It's just one of them. You can do many other different types of schedulers too. Okay. Scheduler classes enable different pluggable algorithms to coexist, scheduling their own types of processes. Each scheduler class has a priority. The base scheduler code, which is defined in kernel sketch.c, iterates over each scheduler class in the order of priority. The next highest priority scheduler class that has a runnable process wins, scheduling who runs next. The completely fair scheduler, or CFS, is the registered scheduler class for the normal processes called sketch normal in Linux and sketch other in POSIX. CFS is defined in kernel sketch fair.c, and the rest of this section discusses the CFS algorithm, and is germane to any Linux kernel since 2623. We discuss the scheduler class for real-time processes later in the section. Oh, okay. So it's not only that you have one fixed scheduler in the system, you can have multiple types of schedules depending on what type of process it is. So if it's like a scheduler or a process that has like nice values and whatever, it's going to be the CFS in this kernel version. And then if it's a real-time process, it's going to use the real-time scheduler, or the scheduler class for the real-time process. I need to be careful with my words. Okay, cool. Okay. Process scheduling in Unix systems. To discuss fair scheduling, we must first describe how traditional Unix systems schedule processes. As mentioned in the previous section, modern process schedulers have two common concepts: a process priority and a time slice. Time slice is how long a process runs. Processes start with some default time slice. Processes with a higher priority run more frequently and on many systems receive a higher time slice. On Unix, the priority is exported to user space in the form of nice values. This sounds simple, but in practice it leads to several pathological problems, which we now discuss. Ooh, scary. First, mapping nice values onto time slices requires a decision about what absolute time slice to allot each nice value. So basically, given each nice value from like -20 all the way to 19, like what is the time slice for every one of these? Like if it's -20, what's the time slice? If it's like -19, or if it's like 5, what is the specific time slice? This is suboptimal. So this leads to suboptimal switching behavior. For example, let's assume we assign processes of the default nice value 0 to a time slice of 100 milliseconds, and processes at the highest nice value, the lowest priority, which is +20, a time slice of 5 milliseconds. Okay, 5 milliseconds and 100 milliseconds. Oh, I think it's like 5 milliseconds. Okay, whatever. I'm having a hard time understanding how that is. Oh, that's true. It has a smaller time slice in this case. Okay, yeah. That makes sense. Okay, further, let's just, because it only has 5 milliseconds to run in this world where we map nice values to time slice values, which is what they're saying is not optimal. It's not the right way to do it. Okay. So further, let's just, so I'm assuming like one with a lower nice value, like a really low one, which means high priority gets a longer time slice in this case, which is, I guess, high, like more than 100 milliseconds, for sure. Further, let's assume one of each of these processes is runnable. Our default priority process receives 20 out of 21, which is 100 out of 105 milliseconds of the processor. So receives 20 out of 21 percentage, whatever, of the processor. Whereas our low priority process receives 1 out of 21 of the processor. We could have used any numbers for this example, but we assume this allotment is optimal since we chose it. Oh, okay, it's right because we decided it's right. So now what happens if we run exactly 2 low priority processes? We'd expect each receive 50% of the processor, which they do, but they each enjoy the processor for only 5 milliseconds at a time. Oh, okay. You get 50% of the processor, but you're only, since you're bounding or you're binding of time slices to nice values, you really only get 5 milliseconds at a time. So you only get like 10 milliseconds total. So then you don't really get much work done at that point. That is, instead of context switching every 105 milliseconds, we now context switch twice every 10 milliseconds. Okay, so you 5 milliseconds, context switch, 5 milliseconds, context switch again, back to the first one, and so on. So you're doing a lot of context switching. Conversely, if we have two normal priority processes, each again receives the correct 50% of the processor, but in 100 millisecond increments, neither of these time slice allotments are necessarily ideal. Each is simply a byproduct of a given nice value to time slice mapping coupled with a specific runnable process priority mix. Indeed, given that high nice value, which is low priority processes, tend to be background processor intensive tasks, while normal priority processes tend to be foreground user tasks, this time slice allotment is exactly backward from ideal. Okay, so that's why we do not bind time slices to nice values because of this type of effect. You either context too little or too much. Context switch, sorry. Okay, so a second problem concerns relative nice values again and again. Well, and again. A second problem concerns relative nice values and again the nice value to time slice mapping. Say we have two processes, each a single nice value apart. Ooh, okay. Two processes, a nice value apart. So let's assume they are at nice values 0 and 1. So only one value apart. This might map, let's say, to time slices of 195 milliseconds respectively. These two values are nearly identical, and thus the difference here between a single nice value is very small. Now instead, let's assume our two processes are at nice values 18 and 19. This now maps to time slices of 10 and 5 milliseconds respectively, the former receiving twice the processor time as the latter. Oh, okay, so yeah, when you're like 0 and 1, it's like 195 milliseconds. But then when you get higher up, where the process becomes lower priority, holy crap, now you're at like 10 and 5, and that's like 2 times more over the other. Okay, so because nice values are most commonly used in relative terms as a system call accepts an increment and not an absolute value, this behavior means that that nicing down a process by one has wildly different effects depending on the starting nice value. So it's really dependent on what the nice value is when you change a nice value by one. You could potentially give it twice as much time in the time slice, or actually just affect the time slice just a little bit. Right? If it's like starting at 18 and you increase the nice value to 19, you've effectively shaved the allowed time slice by half, which is not very ideal. Versus like here, you start at 0 and you increase it to 1, you just lose 5 milliseconds off of like 100. So it's relative. Okay, so and that's really inconsistent and it creates a lot of mystery. So third, if performing a nice value to time slice mapping, we need the ability to assign an absolute time slice. This absolute value must be measured in terms that kernel can measure. In most operating systems, this means the time slice must be some integer multiple of the timer tick. Okay, this will be talked about later on, chapter 11. So this introduces several problems. First, the minimum time slice has a floor of the period of the timer tick, which might be as high as 10 milliseconds or as low as 1 millisecond. Second, the system timer limits the difference between the two time slices. Successive nice values, meaning like 0, 1, or like 18, 19, right, might map to time slices as much as 10 milliseconds or as little as 1 millisecond apart. So it kind of is smaller than like the granularity of the tick, like the system overall. So then you're not really accurate to begin with. Finally, time slices change with different timer ticks. Okay. All right. Okay, so the fourth and final problem concerns handling process wake up in a priority-based scheduler that wants to optimize for interactive tasks. In such a system, you might want to give freshly woken up tasks a priority boost by allowing them to run immediately, even if their time slice was expired. Although this improves interactive performance in many, if not most situations, it also opens the door to pathological cases where certain sleep wake up use cases can game the scheduler into providing one process an unfair amount of processor time at the expense of the rest of the system. Most of these problems are solvable by making substantial but not paradigm shifting changes to the old school Unix scheduler. For example, making nice values geometric instead of additive solves the second problem. And mapping nice values to time slices using a measurement decoupled from the timer tick solves the third problem. Okay? But such solutions belie the true problem, which is that assigning absolute time slices yield a constant switching rate with variable fairness. So yes, you get the bottom line is we don't want to assign time slices to nice values. That's the fundamental problem because you affect fairness this way. The approach taken by the completely fair schedule is a radical rethinking of time slice allotment. Do away with time slices completely and assign each process a proportion of the processor. CFS thus yields constant fairness, but a variable switching rate. So everybody is fair, but then whether or not you execute this time or next time, it's up in the air. Anyway, yeah, I think that's all I had for reading today. And I want to just quickly use the rest of the time to kind of check out how stable my kernel is. My kernel changed from last time. Yeah, so we left off here, and I think we don't have much here. It's still the same. So I do want to kind of take some time to see if we can make the kernel compile faster next time. I'm not sure how do we even do that. Like, I'm just gonna assume that it's just doing that menu config thing and just unchecking more stuff. So if I could do make menu config or something like that. Okay. Can we just like disable more stuff here? Oh, okay. So can we just uncheck ext2? I don't know. I don't know if anybody wants. You can just turn off this now. This video. Not interested. I'm just gonna quota support. Maybe useful later. File system and user space support is important. Character device and user space support. That seems very important. Caches, CD-ROM, DVD file system. Oh, I don't think we need any of this stuff. Okay. Pseudo file system miscellaneous. What is miscellaneous? ADFS, Amiga, Decrypt. These are all modules though, so I don't know if it matters. At least we can get away not compiling the modules later. It is a lot of stuff though, huh? Squash FS. I don't know what that is. We just get rid of stuff that sounds like we'll never use. Network? Oh, we need all this. Andrew, I heard, is pretty good. Plan 9, probably not. Okay. Partition types. Acorn, no. Alpha, no. No, no, no. Guess all this we don't need. Oh, I think these are too important. Maybe it sounds important. Okay. Native language support. Wow. Okay. Oh my goodness. How do we do this? Let's keep that for now. How about, I don't even know if this will make a difference, to be honest. So just hope that it will. Device drivers. These all kind of look important, but I'm just going to say, you know what? We're on a VM anyway. We don't need sound cards. And we don't need ultra wideband devices. That doesn't really sound. Oh, I guess we do need it. Do we? Can't get rid of it. Huh. Sony memory stick. Nope. InfiniBand. Nope. Uh, okay. I don't know what these are. Network device. These kind of look important, so I'm not gonna mess with it. Um, Multimedia support. We were here, weren't we? Wait, where am I? Oh, okay. I think we're already here. Tuner modules. Don't need that. Don't need video capture. Okay. Oh, DVB. We don't need any of that. Okay. I don't know what DA USB is. Okay, so here are a bunch of video card stuff. Guessing Epson's not needed until Carrillo Ranch. I'm hoping to be truck acceleration, not thing. I don't know. A lot of VMs like to use this S3 thing from the past what I've seen. So, Imagination Cairo, no. Fujitsu, no. Toshiba, no. Silicon Motion, no. Another Fujitsu, no. E-Ink. These are all modules, so maybe it'll just speed up the module compilation at least. Okay. Firmware drivers, that looks important. I'm not going to touch that. I think that's okay. Okay. That all looks important too. Maybe it speeds it up just a little bit. So save. Okay. I'm just gonna do something. Can I do a recon? I'll just rebuild it. See if it feels faster. But I'm not gonna record that. So I should have seen how big that kernel was. Okay, whatever. Okay, so yeah, we'll continue with more stuff tomorrow. I'm just gonna build this one more time and maybe report back if that even made a difference. So we can actually move faster next time around. All right, see you.